Hello everyone. Thank you for attending the BAS Electrochemical Webinar 2023 Summer. I'm Miho from International Sales Team, and I will be the moderator. Today, it will be the 7th lecture of a series of lectures in the field of coordination chemistry and electrochemistry, introducing basic electrochemical methods and application, with a focus on organic complexes, introduced by Professor Masa-aki Haga from Chuo University. Today's theme is coordination chemistry and electrochemistry, side-state redox potential electrochemoluminescence.
Hello again, this is Masa-aki Haga. I've talked about many different topics, focus on not only cyclic voltammetry, but also other electrochemical techniques. When you were conducting electrochemical experiment, you came across many questions and troubles. I hope this seminar may help you solve any trouble and questions. Further, you should know new technique to get the new chemical information from different point of view. Today, I'm talking about the redox potential in excited state and electrochemoluminescence. This is a list of my previous seminar topics which I have talked. If you have missed the topic which you are interested, you can watch the webinar site from the BAS website. Today, I will talk about excited state redox potentials. Recently, photoredox catalysts have drawn much attention in organic chemistry as game changers. 2 years ago, the Nobel Prize Chemistry Award goes to Professor David Macmillan and Benjamin List. In particular, David Macmillan has been used the ruthenium and iridium complex as photoredox catalyst. Macmillan Group reported protocol for the direct alkylation of alpha-amino CH bond using cyanobenzene derivative as the coupling partners and iridium complex as a photoredox catalyst. The photoredox cycle is shown in this scheme. In the proposed mechanism, initial reduction of cyanobenzene by excited state iridium ppy3 generated radical anion 7 and iridium 4 state. The iridium 4 species can readily oxidize an alkyl amine, and the resulting radical cations can then be deprotonated to generate the amino radicals 6. The radical coupling between the long-lived persistent cyanobenzene radical anion 7 and the transient alpha amino radical 6, followed by elimination of cyanide, produce the benzoic amines produced product in a highly efficient manner. This general protocol is applicable to a wide range of organic substrate, in particular pharmaceutical relevant compounds that are typically difficult to produce by conventional coupling technique. Recently, big chemical companies use this photoredox catalyst to produce chemical product in a large manufacturing scale using LED light. In this reaction, we should know how the photo-induced single electron transfer occurred. Another example is the dye-sensitized solar cell using ruthenium complexes. This is called Gratzel cell. named after the inventors. In this solar cell, ruthenium complex dye, as shown here, which possess dipyridine or terpyridine ligand with carboxylic group as anchoring group, are immobilized on microporous titanium oxide surface. This ruthenium complex was excited by visible light, which induced the electron injection into titanium oxide conduction band, and the electron goes to the anode electrode through the connecting wires. At anode side, iodine was oxidized to iodide ions, and electron cycle was closed. The key point is the photoelectron injection into titanium oxide. Therefore, the excited redox potential of ruthenium complex and titanium oxide conduction band energies play an important role. In these studies, it is important to determine the potentials of the complex which is excited by light. So, today's seminar is focusing on the topics how to determine the excited state redox potentials. At first, I would like to review again the electron transfer between the molecules and the electrode at the ground state, and the relationship between the Fermi level of the electrode and the HOMO-LUMO energy level of the molecules. When a negative potential is applied from the equilibrium potentials, the Fermi level rises, and when it approaches to the LUMO energy level of the molecules, electron transfer flow from the electrode to the molecules, and the cathodic current is observed. On the other hand, when the potential is swept in a positive directions, and the HOMO level is approached, electrons are transferred from the molecule to the electrode, and the molecule is oxidized. In this case, an anodic current is observed. Therefore, HOMO-LUMO energy of the molecule can then be estimated from the redox potentials. Here shows a voltammeter of ruthenium trisdipyridine 2+ in acetonitrile, which is often used for photoredox catalyst. An oxidation wave from ruthenium-2 to ruthenium-3 is observed on the positive potential side, and the 3 consecutive one-electron reduction waves are observed on the negative potential side as a reversible process. We should consider the photoexcitation of the molecules. Here is the energy diagram of the molecules, which was illustrated by Polish physicist Alexander Jablonski. The horizontal line indicates electronic state and associated vibrational state. This Jablonski diagram illustrated the pathway for the excited electron, by which a molecules emit light or lost energies and deactivate after excited by light. Squiggly line indicate the non-radiative process. Molecules in the ground state are excited to the excited singlet state. Excited electron relaxed from the highest energetic vibrational state to the lowest state, and then emitting fluorescence, or due to intersystem crossing, a triplet state from which phosphorescence is emitted. The timescale for each are picosecond to nanosecond for fluorescence and microsecond to second for phosphorescence. The spin state in the excited state is important. Singlet has the antipolar spin, and triple state is the polar spin state. Further, triple state is quenched by the oxygen in the air. Therefore, Jablonski diagram is widely used in fluorescence spectroscopy to illustrate the excited state of molecules and radiative and non-radiative transition that can occur between them. This is the energy level cartoon for the ground state and excited state. The black circle indicates the electrons. The pink and blue arrows show the removal of electrons at the oxidation and reduction. In the ground state, the oxidation potential is defined as the energy for the removal of the HOMO electron. But in the excited state, the removal of excited electron at the LUMO level corresponds to the oxidation potential at the excited state. In other words, the energy of the excited state E00 is subtracted from the energy of the oxidation potential at the ground state. On the other hand, the reduction potential of the ground state is the potential for the electron to enter the LUMO level. But in excited state, the electron can be accepted into the vacant hole from which the excited electron has exited, so this level becoming the reduction potential at the excited state. Theoretically, the excited state redox potentials are calculated by this equation, called Lambert equations. E00 is the energy gap between the ground and excited state, which estimated from the phosphorescence transition energies. Now, the absorption and emission spectra of ruthenium dpy3 2+ are shown in these figures. In the absorption spectra, the pi-star transition of dipyridines and the MLCT transition are observed in the UV and visible regions. The corresponding phosphorescence emission is observed at 620 nanometers. Now consider the microscopic view for the spectral MLCT transition and the electrochemical reduction process. The optical absorption is the charge transfer process from the central ruthenium to the peripheral ligand. On the other hand, in the electrochemical redox process, the oxidation occurred at the central metal ruthenium from 2 to 3 state and no significant effect on the peripheral ligand. In the reduction process, the reduction takes place on one dipyridine ligand, and 3 redox waves observed in CV due to the sequential reductions of the other 2 ligands. Now, the absorption and emission of ruthenium dipyridine 3 2+ can be quenched by various electron donor or acceptor in solution. Depending on the donor and acceptors, there are 2 quenching mechanisms. One is oxidative quenching, which occurred in the case of methyl biologen, as shown here. On the other hand, reductive quenching occurred in the excited state in the case of methyl phenothiazines. This is a red crystal of ruthenium dpy3. in the solution of ruthenium dpy3, the addition of quenchers induced the decrease of emission intensity depending on the added concentration of the quenchers. From this emission change, the plot of the ratio of emission intensity versus initial intensity against the concentration of quencher, which called Stern-Bolmer plot, provide the quenching rate constant. Plotting the logarithm of the quenching rate constant versus the free energy of electron transfer from the redox potential of quenchers give these curves. By analyzing this curve by the equation based on the Marcus electron transfer theory, the excited state potential was determined. The potential of photoexcited molecule was measured using the phase modulation voltammetry technique because it is necessary to observe the electron transfer between the photoexcited state molecules and the electrode. Normally, excited molecules in vicinity of gold or platinum electrode are considered to be quenched by the electrode, but it has been found that photoelectron transfer reaction in the excited state can be observed when the lifetime of the excited state molecules is long enough. Therefore, the method used here is to cut off the incoming light with choppers and recorded the photocurrent only at the time of incident with the locking amplifiers. Schematically, if the HOMO-LUMO electron exchange in excited state of the electrode and the molecules is equal, the total current is not observed. However, when the potential is received to the positive side, electron in the LUMO undergoes electron transfer to the empty electrode conduction band, and the reduction current is observed. This potential on the positive side of this time indicates the reduction potential at the excited state. On the other hand, when the potential is received to the negative side, the Fermi level of the metal rises and the electron transfer occurred from the valence band to the SOMO of the molecules. The potential at this time is oxidation potential of the excited state. One example is shown in this portogram for zinc porphyrin. Linear sweep portogram of zinc porphyrin at the ground state shows sigmoidal curve, which gives the oxidation potential of 0.36 volt. The linear sweep voltammetry under light irradiation exhibit a peak at 0.22 volt, and no plateau region is observed. This is because the concentration of zinc porphyrin decreases due to the oxidation. Therefore, the reduction potential at the excited state was estimated to be 0.12 volt. Another example of phase modulation portogram is the measurements of ruthenium dpy3. In this case, the laser light is used as the excitation light source. As shown here, the clear response due to the light irradiation were observed on both positive and negative side. From this portogram, excited state potential were determined. This method can observe in the electron transfer between electrode and excited molecules if the lifetime of the excited state is 500 nanoseconds or longer. From these data, the potential shift of ruthenium dpy 3 plus by photoexcitation is shown in this scheme. The oxidation potential in the ground state is plus 1.29 volt versus NaH, which is shifted to minus 0.81 volt by photoexcitations. The first reduction potential in the ground state is minus 1.33 volt, which is shifted to plus 0.77 volt under photoexcitation. This indicates ruthenium dpy 3 becoming a stronger reducing agent and at the same time stronger oxidizing agent under photoexcitation. Therefore, ruthenium dpy 3 can act as an electron donor or acceptor under the photoexcitations and used as a photo-redox catalyst. One example of reaction using ruthenium dpy 3 as a photo-redox catalyst are shown here. It is the photoreduction of the methyl malonate with BNaH, a well-known model compound of NADH in living organisms. In this reaction, when ruthenium dpy 3 is photoexcited, ruthenium is reduced to the monovalent cation by reductive quenching of BNaH. Since this chemical species is highly reductive, it reduces malonate to form cationic anions. The BNaH radical cation also loses protons and is further oxidized to BNaA. The reduction proceeds in over 90% yield. Recently, it has been found that various organic reactions can be induced by a single electron transfer reaction process using ruthenium dpy and iridium complex, which can be efficiently carried out with a very weak LED light, and the process is now being commercialized. Photoelectron transfer in ruthenium dpy derivative is also used for the mimicking biological photosynthetic systems. Here we present our work on a ternary ruthenium dpy, two acceptors linked charge separation systems, connected ruthenium to diimide and osmium-3 hetero dinuclear complex. The middle diimide was naphthalene diimide used. Here shows the cyclic botanogram of ruthenium PNDI osmium triad complex in acetonitrile. There are two oxidation peaks which can be assigned to osmium-2,3 and ruthenium-2,3 couples from the lower potential side. From the reduction process, there are 5 successive peaks. At first, PNDI reductions, followed by the second PNDI reductions, and then DPI ligand reduction waves followed. In the spectral electrochemistry associated with the reduction of PNDI in the first reductions, absorption specific to PNDI radicals is observed at 600 to 800 nanometer regions. also, in the oxidation of osmium in the first stage, the ST absorption characteristic for osmium-2 at around 600 nanometers disappeared, and the second oxidation, MLCT absorption at 400 nanometers disappeared. Here shows the transient absorption spectral change of ruthenium-2 PNDI osmium-3 complex when photoexcited with pulse light. Immediately after the photoexcitation, a new absorption and a large breathing of MCT absorption are observed around 600-800 nanometer region. After that, the absorption at 650 nanometers increased. This spectral change can be interpreted as a photoelectron transfer from ruthenium to PNDI, which lead to the electron transfer shift to the osmium-3. In other words, it indicates the charge separation state is long-lived. Here is the energy diagram of ruthenium PNDI osmium triad systems. Photoexcitation of ruthenium-2 first lead to the electron transfer to PNDI site, and then to the electron transfer from PNDI to osmium-3. This charge separate state energies is 0.42 volt above the starting state. Thus, the determination of potential of photoexcited state is very important to consider the driving force of electron transfer process and also the key to controlling electron transfer and energy convergence. Now I move to the second topic, electrochemiluminescence, ECL. Electrochemiluminescence is a kind of luminescence produced by electrochemical reaction in solution at the electrode. The electrochemically generated species undergo a highly exergonic reaction to produce an electrochemically excited state that then emits light. ECL has been used in various analytical applications, including clinical diagnostics such as DNA chips and cell imaging, environmental assays such as food and water testing. ECL is heavily used commercially for many clinical lab applications, so I would like to show you a short introduction of this technique. When the ruthenium DPY3 in organic solvent is electrolyzed using the two electrode cell, the reduction occurred on the cathodic side produced ruthenium DPY3+, and other side oxidation occurred producing ruthenium-3,3+. When both species diffused into the bulk and encountered each other's, electron transfer and annihilation occurred. One of the two ruthenium species remained energetically and excited, resulting in luminescence. This is electrochemiluminescence. When an electric potential is applied, it is commonly used alternating change in the polarity of the electrode so that oxidized and reduced species are generated near the electrode to increase the collision probability. This is the emission spectrum measured by sweeping the wavelengths of luminescence emitted. when the potential is alternating applied between plus 1.7 volt and minus 1.6 volt at 0.2 Hz. It can be seen the bulk emission specters and electroluminescence specters coincident. Recently, efficient ECL emission is observed under the ambient conditions using platinum electrode in electrochemical nanogap devices. Previous ECL based on annihilation mechanism using the rapid pulsing a single electrode between the oxidizing and reducing potentials suffer from the drawback by the large charging current. The different electrode setup has been used to overcome this problem, such as ring disc electrode, band array thin layer cell. From these studies, annihilation occurred more efficiently at the smaller inter-electrode distance. However, so far the distance was limited at 2 microns. In these studies, using nanogap device with 100 nanometer distance improves the ECL efficiency dramatically. By changing the potentials when the bottom electrode potential is set at 0 volt and top is plus 2 volt, redox cycling occurred for the ruthenium dipyridine. When the bottom electrode set minus 1.5 volt, enough to reduce to ruthenium 3 plus, ECL was observed efficiently because of the short diffusional distance between the two electrodes. So, nanogap electrode setup is a powerful tool for ECL devices. For ECL, another mechanism was developed, a single potential setup using co-reactant. Co-reactant is a species that under oxidation or reduction produce an intermediate that can react with the luminophore to produce excited state. The most well-known combination is the ruthenium dipyridine 3 2 plus trinormal propylamines systems. Both ruthenium complex and amine are oxidized, and the oxidation of TPA generated short-lived TPA radical cations, which lose a proton from alpha carbon to form strongly reducing intermediate TPA radicals. This radical reduces ruthenium DPI 3 plus to form excited state ruthenium DPY 2 plus. This ruthenium 2 plus TPA system is used many biological applications containing many commercial available bioassay devices. One example is ECL immunoassay device for DNA proof for PCR test. In this system, microarray tip has many wells in which 10 spots, and each spot was immobilized on antibody, and the ruthenium complex level by antibody-antigen interaction selectively occurred, and the ruthenium side was monitored by ECL intensity. This is a commercialized instrument and used in medical diagnosis. Today, I talked about redox potential at the excited state and how to determine excited state redox potentials. This information is important for design the photoredox catalyst, which is one of the rapid progress area. Much research is going on. Related to the excited state, I also talked to the electrochemoluminescence. It has two ECL mechanisms. One is the annihilation mechanism, and the other is co-reactant mechanism. The ECL is a powerful tool for bioimmunoassays. Here is a reference for photoredox catalyst and electroluminescence. So if you're interested, please read it through. Thank you.
Thank you, Professor Haga. If you have any question regarding to the lecture or other topics, you can contact us. In addition, the movie of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news. Also, you can watch the Professor Haga's past 6 lectures. The next webinar is already scheduled for October 4th. For today, thank you and have a nice week.